our topic is quantum mechanics. How quantum mechanics originate from the in our daily physics, or from start where we can start the quantum mechanics. What is the problem of the basic physics? That's why we need quantum mechanics to solve this problem. So first we have to talk about this. Before starting the quantum mechanics, the known physics was made with classical mechanics. Second one, electrodynamics, classical electrodynamics. And third one is the calculus or mathematical physics. Before starting the quantum mechanics, the fundamental physics was made with this classical electrodynamics and mathematical physics. And who are the supremo in this domain? Especially if we talk about the classical physicists, then a lot of mathematicians or physicists are there. Obviously Newton, then Lagrange, then Hamilton, this kind of. And if we talk about the classical electrodynamics, the main legend was Maxwell, Faraday. So using this thing, we can establish our daily life experience or any kind of classical observation. We can explain it properly. But if we study about radiation, first problem was, if we talk about radiation, first problem was, if we see the graph of the radiation, energy versus wavelength distribution, then we observe that the nature of the radiation is continuous in nature. But to explain this with the help of classical physics, it is too much difficult. Why it is too much difficult? Because we have not that much idea with the interaction of radiation with matter due to the lack of quantum mechanics. How the question generates here. Many important questions, 2-3 questions are there. One, we can't say that for a particular energy distribution of a black body, we cannot assume that it can consist of lot of wavelength. We cannot, using the classical physics, we cannot assume that consistent of lot of wavelength that can give that kind of distribution. There is a main discrepancy. Means at first they assume that at a particular lambda the radiation is covered by the black body. So first thing is it depends on temperature and winds. Assume that scientist winds assume that the radiation of the black body depends on temperature. That is one thing. And another thing is radiation quantity is invariant. Radiation quality, not quantity, radiation quality is invariant with respect to the energy of the system. So how there is some ambiguity in this concept. How can we introduce this kind of thing? Let us consider if we talk about the Wien's theorem. According to Wien's theorem, it depends on temperature, and the black body can be consist of a particular wavelength. The energy distribution should belong within a particular wavelength region. But actually, if we see the curve, the energy is distributed among lot of wavelength range. So, if we talk about the Wien's conditions, so let us assume within a black body, let us assume one blue ray and one red rays falls on the black body, and we talk about two objects, one is B and one is R. B object can absorb blue light and red object, R object can absorb red light. If we imagine that there is a less amount of blue ray, or there is insufficient amount of blue ray, and enough, if we provide enough red ray, so we can tell that the red object, the R object, can absorb more amount of heat, and blue object definitely it loses heat because there is a deficiency of blue rays. Now, if we consider it is an isolated system, then what will be the condition? This is the blue, this is the red. If we isolate this, then we can imagine there is a temperature difference, because we know that due to fall of the blue and red ray, there is a deficiency of blue ray. So blue ray temperature is lesser, and consider T2, and red object has temperature T1. So as they have a temperature difference within the evacuated chamber or isolated chamber, so we can consider as a Carnot cycle. It is a Carnot cycle. So from the cycle we can tell that some work, some mechanical work can be extracted from the system, as it act as a heat engine. So we can extract some mechanical energy from the system. Now, if we remove these two balls, two objects, after that again if we put this and do the same process, so we can say that infinite amount of energy we can an infinite amount of mechanical energy can be extracted from the this fixed system. That violates the second laws of thermodynamics. So that is the radiation. So if we make intact the radiation, means if we don't want to change the wavelength of the radiation, or if we don't want to change the quality of radiation, so we have to repeat this process such that we can extract same amount of energy, but it violates the second law of thermodynamics. So we cannot assume that within a black body only one wavelength will be there. So there is a series of wavelength consisting inside the black body region. That is the one discrepancy. Another discrepancy was from the radiation theory. From Wind's law we know that lambda t equal to constant. So at a particular temperature, at different temperature we can find different wavelength inside the black body. It has a different application. We can calculate the temperature of any celestial object using this formula. But problem was, it can explain nicely for the higher wavelength region. The black body radiation can be explained nicely at the higher wavelength region. But for the lower wavelength region, we can't explain using this theory. So, how we can explain this? Now, Rayleigh, a renowned scientist, he proposed an idea. He proposed that if we consider this type of radiation as the superposition of the radiation is considered as a wave, and using the superposition principle of wave, we can calculate the energy of the system. So using this theory, we can calculate the energy distribution. dE will be equal to, as we know that if we this is the classical stage of physics, so the energy in every degrees of freedom, we know that it is kT. It is kT, and the number of waves or number of nodes presents inside the wavelength region mu or frequency region mu to d mu region is 4 pi mu square d 4 pi mu square d mu. So if we calculate this 4 pi mu square d mu, if we calculate 0 to infinite range, so we can get, if mu goes to infinite, then, or if we consider it is a wavelength, so it will be 4 pi lambda square d lambda. So if we go to the at infinite wavelength, if we go at the infinite wavelength, then this energy will be infinite. That means this curve has asymptotic approach.